Everyone, my name is Kevin Bach from the University of Maryland. Before I get started, I just wanted to give a huge shout out to all of the SIGCOMM organizers for making this event happen, despite everything going on. I also want to just give a big thank you to all the collaborators on this project. It's really taken a village to pull this off. So today I'm going to be talking about censorship, and specifically a new form of censorship evasion that we've been working on, server-side evasion. Now, before I get into this, I'd like to give you a quick background on in-network censorship done by nation states. So there's many types of censorship that operate around the world today, and I'm going to be talking about the automated form that operates within the network. So some nation states operate censorship like this, where they're physically in the path. Other nation states operate censorship like this. So instead of being in the path, they're on the path. Now, if the client makes a forbidden request here, this request will move through the network. The server will get the packet, but the sensor will too. So if the sensor wants to censor this connection, it can't just drop it because it's not in the path. So instead, what it will do is it performs deep packet inspection. If it determines this is something it needs to censor, it will inject spoofed teardown packets. So specifically, these are TCP reset packets. These are normal packets our computers send all the time. And they exist just to tell the other side, stop talking to me. And it's going to send two of these packets, one in each direction. It's going to send one to the client, pretending to be the server. And it's going to send one to the server, pretending to be the client. And what's going to happen is the client is going to get this packet and think, well, the server just terminated our connection. And the server is going to get this packet thinking, well, the client wants to stop talking to me. And just like that, both sides stop communicating with one another and censorship has been achieved. So to inject these teardown packets, though, the sensor requires some information about the connection, right? Like you need to know the port numbers, the sequence and acknowledgement numbers, etc. So that means that the sensor is tracking per flow state. And if the sensor is tracking per flow state on the scale of an entire nation, it will necessarily have to take some shortcuts along the way. And we as evaders can take advantage of these shortcuts. So I'll show you an example of what this can look like. This example is from prior work. So here's our client again, about to make a forbidden request, let's say again in China. But before it makes its forbidden request, we're going to inject a packet of our own. This is a TCP reset packet of our own. We're going to send it in such a way that we set the TTL, or time to live. This is a field in the IP header that controls how long the packet survives in the network. It decrements once per hop. We're going to set the TTL high enough such that it reaches the sensor, but not so high that it reaches the server. So when we send this packet, again, this will move through the network. But in this case, the server is not going to receive it. It's going to get dropped along the way. But the sensor will receive this packet. And when the sensor sees this packet, it thinks, well, it looks like the client just shut down its connection between the client and server. I can stop tracking this connection now. And it throws away the state it's maintaining of the connection. Now, the server never even knew we pulled off this trick. So at this point, the sensor is no longer monitoring our connection. The server thinks we're good, and for the rest of this flow, the client and server can communicate censorship-free. Now, this is just one example of many that have been done in the past in prior years. And one thing that's held all of these techniques in common is that evasion has always involved the client. And even censorship evasion techniques that do not rely on manipulating your packet stream specifically have this requirement. Tor, VPNs, proxies, they all require the client to do something. And usually that something involves installing some sort of software or configuration on their system. The problem with this is it's always posed a significant barrier to deployment. Getting clients to install the software itself can often be a problem. Even just beyond the difficulties of that, often installing the software in the first place can pose risks to the user. And making this problem worse, we can't help users who don't even know they're being censored in the first place, or who may not possess the technical expertise to configure software in such a way that they can defeat censorship safely. So this was the problem we approached this work with. Now, ideally, if we were to try and ameliorate these problems, the servers could help, okay? So we're proposing is instead of deploying software at the client and forcing clients to do these things, we could instead move the software deployment from client to server. The server would then subvert censorship on the user's behalf without the clients needing to deploy anything at all. Now, this sounds crazy, but just think about the benefits of such a system, okay? Out of the gate, we would immediately broaden the accessibility and reachability of censorship evasion. Many clients all connect to one server. Clients would no longer require technical expertise or even to download software in the first place. All these users would get plausible deniability for evading censorship because they're not the ones doing it. And this immediately uncensors all users who didn't even know they were getting censored in the first place. So this sounds incredible, but the problem with this is that server-side evasion shouldn't be possible in the first place. And to see why this is, let's consider a waterfall diagram of the exchange of packets between a client and server before a client is going to make a forbidden request. Okay, so the client is going to start as usual, send a SYN, the server responds with the SYNAC, the client completes the three-way handshake, and then the client makes its forbidden request with the censored keyword. Now the problem is, the only thing a server does before the client gets censored is it sends the SYNAC packet. That's it. So the server has no ability to influence the connection past the SYNAC at all. And just underscoring the difficulty in this space, there's been no prior work whatsoever in evading censorship purely from the server side for these vanilla protocols. So in this paper, I'm happy to say that server-side evasion is in fact possible. And the rest of this talk, I'm going to show you how we discovered these server-side techniques and the results we got deploying this against multiple different countries and multiple different protocols. While we were doing this, we actually got many new insights into how sensors work. And I'm going to call out two of these in this talk specifically with the Great Firewall's resynchronization state and something we've been calling multi-box theory. So before I dive into this, I'm going to give you some background on a tool we used and modified to find these strategies. And this is Geneva. So Geneva is an open sourced client-side tool for automatically discovering censorship evasion strategies. This was originally published by my team last year. So the way Geneva works is it runs strictly at one side and it manipulates packets to and from the client. Geneva is a genetic algorithm, hence its name, and its job is to automatically discover censorship evasion strategies to defeat a censor. Now, it has the ability to manipulate packets inbound and outbound from the side it's running on. And the way it does that is it has 4 actions that it can do this with. So that's duplicate, we take one packet, we make 2. Tamper, we take one packet and change it somewhat. Fragment, we take one packet, we make 2 packets, break the packet in half. Or drop, where we take a packet and drop it on the floor. So I'll call out 2 things specifically here of note. So for tamper, this allows us to alter or corrupt any TCP/IP header fields. And importantly, Geneva it gets the syntax of this. It knows it can change. There's a flag, there's a field flags, for example, that it can change. But it has no semantic understanding of what these fields mean. It sees that it can change a flags field, but it doesn't know that changing it to a SYN means the start of a connection. The second thing to call out is fragment. Fragment does a bit of double duty here. At the IP layer, fragment performs fragmentation. At the TCP layer, it performs segmentation. So we manipulate packets in and out, and we can compose these actions together for broader things. And specifically, the way we can compose these things together is in a tree. And this tree operates in a match action pair. So all trees have a match, and in this case, this matches any outbound TCP flags, any outbound TCP packets with the flags field set. And if this match happens, we run some sequence of actions. So in this case, if we see an outbound TCP packet with the flags field set to A, set to ACK, we pull it into the tree, we duplicate the packet and modify it accordingly. So let's see what this looks like on the wire. So running this strategy from the client side, here we have our client again about to make its forbidden request to the server. And the client is about to finish its three-way handshake. Geneva will catch this outbound ACK packet. It pulls it into the tree. We duplicate it. To one side, we're done. To the right side, we change it to a reset. We change the TTL. And then we do an in-order traversal of the trees and send the packets accordingly. And you'll notice this exactly implements the strategies I told you at the very beginning. So this is Geneva in a nutshell. So for this paper, what we did is we took Geneva and we modified it so that we could run it strictly from the server side. And then we deployed it against real-world sensors. Now, in our previous work and many others, we've tended to focus on HTTP. So in this work, we've actually brought into the protocols we try to subvert censorship for. So to support this diversity of protocols, we needed to automatically trigger censorship for all of these. This usually involves making requests or queries with forbidden keywords or domains. So for example, in HTTP, you could make a request for some forbidden resource. HTTPS, you could stick something in the SNI fields that's forbidden. DNS, make a forbidden query, etc. For SMTP specifically, I'll call this out. All you need to do is you send an email to this email address. For context, this was an email address used to distribute proxy nodes for a popular circumvention system in China. Now, to show that this could be applied broadly, in addition to a diversity of protocols, we also apply this to a diversity of sensors themselves. And we ran Geneva against all of these sensors for all of these protocols. This is China, Iran, Kazakhstan, and India. I'll call out one thing up here, that Iran, even though Iran censors DNS, for the vantage points available to us, DNS over TCP was actually not active. So DNS over TCP was not censored from our vantage points. And for that reason, we were unable to test it. So recall that despite this breadth, server-side evasion shouldn't work in the first place, right? All a server does in all of these cases before getting sensors is send a SYNAC. And in all these cases, it's unable to influence the connection past the SYNAC. But despite this, Geneva found strategies, and here's one of them. So here's the first example of a successful server-side evasion strategy. This one works in China, and there's a lot going on, so I'll break this down. As usual, the client starts by sending a SYN, but instead of responding with a SYNAC as usual, the server responds with two SYN packets. So first it sends a normal SYN, and then it sends a SYN with some random payload. So this first SYN packet serves to trigger a TCP simultaneous open. This is actually an archaic feature of TCP that's supported by every major platform today still. And this was built just to handle the case in which two computers sent a SYN packet to each other at the exact same time. Now, when the client receives this first SYN packet, the RFC mandates that the client then sends a SYNAC packet. And it's this combination of this second SYN with a payload, followed by the client SYNAC packet, that causes the Great Firewall to desynchronize from the connection. And for the rest of this flow, the client and server can now communicate censorship-free. Now again, this seems crazy, but this actually works with varying degree of success across all of the protocols we found. And for context, the baseline success rate for censorship evasion in China, should you do no strategy, is around 2%. So this is one successful strategy, but it's actually just one of many. We were altogether found 11 different strategies. We discovered 8 in China, 1 in India and Iran, and then 3 in Kazakhstan. Now the paper goes into detail for all of these, and I don't have time to go through them all here, unfortunately, but I would love to show you just a few more. So the next 2 will take place in Kazakhstan. So this first one is fun, it's very straightforward. As usual, the client initiates the connection with the SYN. And instead of responding with the SYNAC immediately, the server simply sends a packet with no TCP flag set at all. And this alone is sufficient to defeating censorship from the server side in Kazakhstan. The sensor simply cannot handle unexpected flags during the three-way handshake. And seeing strategies like this, one of the big takeaways from this for us was to really help motivate why we should be using automated techniques to discover these. This is likely a bug in the Kazakhstani sensor. It may have been difficult for a human to discover. So another example I'll show you, this again in Kazakhstan, and we call this strategy the double benign get. So here too, again, the server changes up the handshake a little bit. Instead of just sending one SYNAC packet, we actually send 2. And within each SYNAC packet, we attach a payload. And within that payload, we put an innocuous HTTP GET request. Now, what this GET request serves to do, when it crosses the sensor, this causes the sensor to confuse the roles of client and server. It thinks that since the server is launching these requests, the server must be the client. And since the sensor processes packets from the client and server differently, by reversing the roles of client and server in the mind of the sensor, this allows us to defeat censorship for the client for the rest of this flow. And this works with 100% reliability in Kazakhstan. So at this point, we've seen many different types of bugs in sensors, everything from not handling esoteric features in TCP correctly, error cases, confusing logic altogether. For more details, I'll refer you to the paper, but I'll remind you and I'll note that none of these require any sort of client-side deployment whatsoever. They may often induce behavior from the client, but no software configuration changes are needed from the client. And to show this, we actually tested this across a wide variety of clients. And throughout all of this testing, we only found one case of a strategy that relied on platform-dependent behavior, and we were easily able to rewrite that strategy to make it platform agnostic. So across the board, we found that these strategies were well supported by every major platform in use today. So all of these strategies, while we're studying these, they teach us a lot about how sensors work. So now I'd like to talk to you some more about the new insights we've gleaned from these strategies. And the first thing I'm going to talk about is the resynchronization state. Now, the resynchronization state is a feature of the Great Firewall of China, so this is in China, that allows it to be more tolerant to packet loss. And specifically the way this works is simply if a middle box misses a packet, for example, some part of the handshake, the sensor can just resynchronize its state later on. Now, the exact dynamics of the resynchronization state, they're constantly evolving over time, but understanding how this state works allows us to build better censorship evasion tools and strategies. And this also gives us insight as to why that first strategy that I showed you works in China, this TCP simultaneous open-based desynchronization. What we find, I'm going to zoom in here on the SYN with the payload, that this SYN with a payload actually triggers resynchronization within the Great Firewall. And the next packet that it's going to resynchronize on is the SYN-ACK from the client. But because the strategy forces a TCP simultaneous open, we found that there's a bug in the resynchronization state in the Great Firewall where it does not properly increment the initial sequence number. And what this means is that this strategy is actually an off-by-one bug in the Great Firewall. Now, amazingly, this does work, but it seems to work very differently protocol to protocol, which is strange. But we found actually that the Great Firewall of China resynchronizes differently depending on the protocol itself. So for example, for FTP, if a SYN-ACK packet is sent with an incorrect ACK number, this will cause the Great Firewall to resynchronize in the next client packet, but only for FTP. For all protocols but HTTPS, if the server sends a reset, we'll resynchronize on the next client packet, but that does not work for HTTPS. For all protocols, we found that if a server sends a non-SYN-ACK packet that contains a payload, it will resynchronize on the next packet that has the ACK flag sent. And this is just the first example of strange protocol variability we found in the Great Firewall of China. And the reason this is so strange is because all of the server-side strategies we're discussing here, they operate strictly within the TCP three-way handshake, which raises the question, why are different applications affected differently in China? Because we've always tacitly assumed that the way the Great Firewall of China works is that it has this very same separation between transport protocols and application layer protocols. But because we're finding things that operate differently at the TCP stack layer, this suggests that the Great Firewall has different TCP stacks for each protocol, which strongly suggests that the Great Firewall is actually running multiple censorship middle boxes in parallel. And this is this multi-box theory we're presenting. So what this looks like, instead of some single monolithic sensor as we've often assumed or pictured it as, there are actually multiple sensoring middle boxes all running together. And this begs the question actually of how does the Great Firewall of China know which middle box it should be applying to the connection? Because it can't just rely on port numbers. The Great Firewall of China censors effectively across any port. So the simple answer of how does it know which middle box to apply is we find that in fact it doesn't. Every middle box will get a copy of the packet independently, okay? And each of them will just be applying protocol fingerprinting. So each of these will examine the packet and say, is this mine, is this mine, is this mine? And then whichever one identifies it as something it can censor, it can operate. This also raises the question, where are these middle boxes located? So in the paper we described, we've used TTL limited probes to try and determine, are these things close to each other? Are they far away? And as far as we can tell, these are co-located at the network level. So they're separate but nearby. So this concludes my talk on server-side evasion. In sum, we show that server-side evasion is possible. We've identified new insights into the Great Firewall of China. All of our code is open source, and I invite you to check it out on our website, geneva.cs.umd.edu. So thank you again.